pitfall. So let's go back now to my 2 alpha glucose molecules, and let's just clarify the issues associated with beta glucose. So we've got alpha glucose at the moment, CH2OH there. So just a reminder, the way I remember alpha and beta glucose, beta is symmetrical or even. So alpha down, up, down, down for alpha, down, up, down, down for alpha. Make that into beta glucose, down, up, down, up. So all I've got to remember is the first one on the left hand side is down. That's how I remember. And then for beta glucose, it's even. I don't have to remember a huge amount more than that. Beta glucose. Well, here's the problem, okay? We want to join these 2 beta glucose molecules together in the same way. Condensation reaction, fantastic, no problem. Condensation reaction, elimination of water, fine. But spatially, the OH group here is above the plane of the ring, and the OH group here below the plane of the ring. That causes a problem, because really we want them to be in the same place to allow them to bond together. It doesn't work like that. What has to happen in order for 2 beta glucose molecules together is for one of them to flip, to be inverted 180 degrees. So this is actually really quite, well, I find it a tricky thing to draw, but I'll do it. Just a reminder, carbon 1, 2, 3, 4, 5, 6. So I've got to sort of kind of do a mirror image of that. So there's my oxygen. It's gone from up there now to the bottom of the ring. I'll put my numbers on here. Carbon 1, 2, 3, 4, 5, and carbon 6 is down here. So I can put my CH2OH on there, not a problem. This on this side was pointing up, but now it's going to be pointing down, and now remember they're symmetric, they're even, so it's going to go down, up, down, up. Okay, so this one was pointing down, it's now pointing up. This one was pointing up, it's now pointing, it's up here, carbon 3, it's now pointing down. This one was pointing down on carbon 2, is now pointing up, and carbon 1, same idea. But now look what we've got. So let's now look, this is now 2 beta glucose molecules together, but arranged in such a way that the second one, in this case, is turned upside down. And look what we've got, the OH groups now are spatially in the same place, so they can bond together. So indeed, they do. Condensation reaction, elimination of water, and we end up with a glycosidic bond. This is called, funnily enough, a beta 1,4 glycosidic bond. Now, that gets repeated over and over. It works better here. So you know on the last one when I showed 2 alpha glucose molecules bonding and then I put an N by them, well, I could really just put 1 alpha glucose molecule and put an N by it. It says this is just repeated over and over again. It works better for 2 here because it's this now is got the repeated unit. 2 beta glucose molecules, one of them flipped the other way, happens again and again and again, and that continues. So why does that really make a difference? Well, let's just look at the OH groups. So the OH groups are what are going to confer the majority of the properties here. Let's just count them up and the direction in which they're going. So I've got an OH group pointing up there. I've got an OH group pointing up there. And on this molecule, I've got an OH group pointing up there. So my OH groups which point up, I've got 3 pointing up. How many have I got pointing down? I've got... Can't count that. Can you tell me why I can't count that? Adam?
Is it because it formed the condensation?
Well done. It's bonded. Same over here. Can't count that. It's bonded. So that's not involved. That's not one that's pointing up or down. It's involved in the bonding. So how many are pointing down? I got this one pointing down. That's 1. This one pointing down. That's 2. This one pointing down. That's 3. I've got the same numbers pointing up as pointing down. If we had done this with, perhaps it's rather obvious really, but if we had done this with 2 alpha glucose molecules joined together, we end up with, we can kind of see it here, it's this repeated, so I'd have 1, 2, and this would be exactly the same, 3, 4, pointing up, and 1, and the same over there, 2 pointing down. So what happens is, you've got, if this is your chain of alpha glucose molecules, you've got more OH groups pointing up than you have pointing down. Now the OH groups are what are going to do the hydrogen bonding. So what happens is that those OH groups bond to each other, and actually what you end up doing, I'll put it this way, is you get a curling of that, or coiling would be better, a coiling of that chain of alpha glucose molecules, and hence we get this coiling, this spiral effect. In fact, the reality is quite difficult to show with on the board because it's 2D, but if I show a coil structure, which is what amylose looks like, no branches, the hydrogen bonds actually exist between sort of adjacent rungs. So I have a hydrogen, there'll be an OH down there and an OH up there, and that's where the hydrogen bond appears. That's what maintains that coiled structure. But it's a consequence as well of having more on one side than the other. The beta glucose joined end to end, it's even on both sides. So what happens is, if we were to draw a chain of beta glucose molecules, there is no bias on one side or another. I'll just show the one OH group on each side. So I've got an OH group there pointing up and an OH group there. OH group, OH group. We know it's even, so I'm just reducing it to 1. So its capacity to bond through hydrogen bonding is the same on both sides, etc. Now, why is that significant? Because if I had another chain of beta-glucose molecules with exactly the same structure, which it's bound to, with OH groups even on both sides, what I end up getting is hydrogen bonding between those OH groups. And we get what we call crosslinks between adjacent chains. So we can call them hydrogen bonds because that's strictly speaking what they're called, but often we will just refer to it as crosslinks. So you get crosslinks between adjacent chains, and that gives the strength to cellulose. And it's a consequence of having these even numbers of OH groups above and below the plane of the chain. Now the wording's got to be spot on here, and this is the bit people lose marks on, the way they word it. So, structure of cellulose. Number 1, long chains of beta-glucose. We could say joined by glycosidic bond, but it's less important. Within a chain, should I say within each chain? I want to be clear, I don't want to be unambiguous. Within each chain, every other beta-glucose is flipped 180 degrees. Hydrogen bonds or crosslinks exist between chains. Okay, now the wording there is important. I'll just tell you why you can go wrong. The key terms of this: within each chain and between chains. Because you frequently will say, oh, structure of cellulose. Yeah, there's hydrogen bonding between beta-glucose molecules. Yeah, there is. Right there, look, there's a beta-glucose molecule there and a beta-glucose molecule there. That's a hydrogen bond, you're right. But it's ambiguous. Give me another version of that. So instead of saying hydrogen bonds between beta-glucose molecules, what else could I say that is accurate? What could I change on there and still be accurate? Rather than saying there's hydrogen bond between beta-glucose molecules. It's the bond that I could change. I nearly said it's the bond that's wrong. It's not wrong. But what could I change? Could I put another bond between beta-glucose molecules and still be accurate? I've seen a lot of blank faces. Doesn't look good for the camera, does it? What's that bond? What bond is that there?
Really.
You can name it. It is a covalent bond. You can actually name it. We just had it on the board in front of us.
Glycosidic.
It's a glycosidic bond. So am I wrong to say that there are glycosidic bonds between adjacent, or just between beta glucose molecules? No, there are glycosidic bonds between beta glucose molecules. So that's why we have to absolutely specify that the hydrogen bonds exist between chains. You could say, exist between beta glucose molecules of adjacent chains. Fine, that's clear. You're saying between the beta glucose molecule of that chain and the beta glucose molecule of that chain. But if you say there are hydrogen bonds between adjacent beta glucose molecules, you would not be given that mark because you haven't been clear. Because you could argue, no, you mean glycosidic. You haven't been clear. So you can say long chains of beta glucose molecules joined by glycosidic bond. Fine, glycosidic bond. Within each chain, probably be better to say within each chain, they are joined by glycosidic bonds, and every other beta glucose molecule is flipped by 180. Between chains, we have hydrogen bonds existing, or cross-links between those chains. Yes, they're between beta glucose molecules, they are, but they're between beta glucose molecules of adjacent chains. When we get lots of these, last thing, lots of these with all these hydrogen bonds, this whole thing here, this sort of macro structure of all these chains is called a microfibril. That's the name given to it. Now I say that, say it's a microfibril, like, okay, yeah, fine, I'll remember that. Do you know what? That comes up in mark schemes all the time. Describe the structure of cellulose. Or why is cellulose so strong? Now I don't think saying microfibril actually tells you why cellulose is so strong. Cellulose is so strong because we've got hydrogen bonds between adjacent chains. Okay, that's the main reason. But there'll be a mark for saying microfibril, and you'll think, I don't know why the hell that's on the mark scheme. Yeah, but get used to it because it's there a lot. So just put it down. It's easy to do. Okay, that structure of lots of chains joined together is a microfibril. I've talked a lot, but I'm going to do chitin, but it's really quick. Chitin, exactly the same. Long chains of beta glucose molecules, yeah. Joined by glycoside bond, yeah. Within each chain, every other beta glucose flipped, yeah. Hydrogen bonds, yes. Exist between chains, yes. All that works, except the one add-on for chitin. Within chitin, some of the OH groups are replaced by amino acids. But we still get hydrogen bonds between amino acids of one chain and the next. That's the difference. Everything else stays the same, beta glucose, but some of the OH groups on the beta glucose molecule, molecules have got amino acids instead of the OH group, but the amino acids can still bond through hydrogen bonds. In which case, it's still hydrogen bonding between chains. Chitin, for what it's worth, you know what cellulose is. It's a structural polysaccharide in plant cell walls. Chitin forms the exoskeleton of insects. Okay, structural, strong, waterproof layer. Where's its strength come from? Same principle. Where do we find it? The exoskeleton of insects. Right.